Now, if our models are wrong, and we're trying to apply an erroneous model to a problem where we keep asking questions, we're not going to get the right answers. So, as Einstein pointed out, one of the things we really should do is always question the model. There's no such thing as a perfect model. We make too many assumptions on the front end. But it sounds kind of dry and kind of boring and kind of silly to ask a question like, what is time? What is mass? Blunt truth of it is, physics does not know what charge is, what time is, what mass is, what length is. None of these things. But they don't tell us that when they're teaching us in school. They come across as if we already have it all figured out and all we've got to do is wind up a few decimal places. Well, that's just not true. What we want to do is not chase the decimal places, but we want to chase the model itself, a little bit of its history, and find out what they actually put in it and what we ought to change today because we've learned a lot since then. Could I have the next slide, please? Basically, we will start in, you might say, physics, and particularly electrical physics. I'll throw in anti-gravity to you for free. That's not going to cost you anything. We'll throw in over unity systems for you. We'll give you the theory of how they work. We will explain what right now I think is the missing ingredients in cold fusion. And then we'll try to turn to what this has to say about living systems, life on planets, and development of living systems, and what kind of scenario evolves for a living system that's also a technological animal. That is, it has a tool-using member, and it makes tools, and therefore has a technology, both for use to overcome its environment and in use against its own self-competition. Next slide, please. These are basic subjects. I won't stand here to read those things to you. We'll give you cold fusion effect. I'll tell you about the use of some of these rather strange waves to give you a totally new kind of healing, and this was proven. I don't have to prove anything. It's sitting in the hard literature in France. All we have to do is get the people to redo the experiments. Next slide, please. Well, science has a history of suppression. The worst enemy of science is organized science itself, and leading physicists of the world generally have always recognized that. In his day, the greatest physicist of the day, Max Planck, said, basically the old guy's got to die out before you can ever have a new physics. It's as simple as that. It still is. Things go 50 years in the literature and are totally ignored. One paper that I'm talking quite seriously about is 1903. It's totally ignored to this day, and it's one of the most fundamental things in the entire literature. Many things are sitting on the shelf, parked in our scientific literature, never examined, never followed up, not in our present models. Some of them forced revisions of many of our most fundamental thoughts. Next slide. Here's an example. It goes all the way back to the 1800s of something that laid fallow for 40-something years. People just didn't have a kinetic theory of gases and so forth, spring, full tilt, and with sweet reason accept it. That's not what happened. 40-something years went by till the old guys who opposed it died. That's how you got that kind of physics. Many of the things you studied in your books in university, Wegener, who discovered the plates in the earth and the movements of the plates, the name Wegener was made the same word as fool, utter fool. People would say, oh, he's a Wegener, which means he's an utter fool. Anybody ever apologize to Wegener? Hell no, like the Cajun says. Next slide, please. And today, it's worse than ever. If you are a young fellow going to college, going to university, and you are curious, scientists are supposed to be curious. Don't be too curious. Unless you pay the freight and learn the subject the way it's taught to you and learn to apply it, you're not going to live and do well, and you're not going to get your doctorate, and neither is the professor who's teaching you and allowing you to do that. He's in a continuous game of putting in requests for money, proposals. Maybe 1 in 8 he gets. If he can't fund his graduate students or he can't fund his own research, and if he can't get his papers published in the literature, he's dead. He may as well go work in a butcher shop. And many of them do. So we have a thing in science where when we use a phrase like the Standard Model, we mean a little more than just people with sweet reason have come to this conclusion. They beat you on the head and take your job. You don't get tenure. You don't become a full professor. You don't get your papers published. Sorry, but that's the way it is. It's not so much a giant conspiracy as it is a dogma. But, you know, it's splitting hairs to go to make the difference. The end effect is the same thing. First, let's talk about what happened to electrodynamics. Now, Tesla, next slide, please. Tesla calls the present electrodynamics we have the most inexplicable aberration of the scientific mind that had ever been recorded in all of history. That did not endear him to the very few scientists, about 3 dozen all there were in those days, electrodynamicists, who were struggling to understand this stuff. But Tesla was right. He was not wrong. I wouldn't have said it that way. That's much too blunt. But he spoke the truth. And I hope to show you a few of the errors that we've just propagated, and nobody ever went back and changed. Next slide, please. Well, electric charge. First, we had a material ether. And then we didn't have a material ether. And the next thing was we didn't think we had an ether at all. So we had the ludicrous thing of a medium undergoing vibrations without a medium. A clothesline undergoing clothesline vibrations but without a clothesline. Now that's what's in electrodynamics today. Electric charge, nobody knows what it is. Over on the right, I show you a good physicist saying we really don't know what it is, but we know what it does. It's become very fashionable in physics to say we don't ask the question what anything is. We ask the question what it does. Our business is not to find out what anything is. And I'm saying, well, then what are you doing? I want to know what the potential is. And quite frankly, I couldn't find anybody, and I asked some pretty good fellows, and the real good physicist would tell me he didn't know, couldn't define it exactly. Feynman will tell you he can't define it exactly, and he does so in his 3 volumes of physics. He tells you don't look for a definition of force. You ain't going to get none, like the Cajun said. So, charge, what in the world is electric charge? Well, I'm going to give you a little quick and dirty definition of electric charge. It's a piece of mass, whatever mass is, that's engaged in a violent energetic exchange with a vacuum. The vacuum is nothing in the world but a seething sea of raw energy. I don't have to prove that no more. Even the U.S. Patent Office has recognized it and issues patents recognizing the vacuum as a source of energy. So help me God, the mountain finally came to Mohammed. So nowadays the vacuum, the energetic vacuum, which is only about 50 years old, been known for about 50 years, been proven for about 50 years, has finally been accepted. Remember that 50-year figure before we get something accepted in the ordinary science. Mass is in fact engaged in a charged mass in a very violent exchange of energy with a vacuum. But it's a funny little exchange. It's a peculiar little bird. It's spinning. It has spin. Now what it does is it doesn't quite reflect all of that back, re-emit it all back as virtual particles. That's a particle that appears so fast and disappears so fast you can't grab it individually, but lots of them make up all the forces that we have if a whole bunch of them get together. They generate all the forces in nature, quantum field theory. So what we have is a little bit of these things like an old spinning wheel. This is a crude analogy. Don't press it too far. But like a spinning wheel takes a little bit of the fibers from the cotton and weaves them into a long thread. This thing weaves some of these little bitty virtual particle changes into coherent changes, groups of coherence, which if they'll hit another particle will make an ordinary observable change, will translate the particle. What did I say with all that mess? I've got to speak 2 ways. Some people here are technical, some people are not. Non-technically, what I said is this thing absorbs a lot of energy, radiates most of it back in the same form, but some of it puts out in the form that generates all the fields and all the potentials and all the energy in those fields and potentials that reach from that charge all the way out to space. Now, this has been known for 40 years in particle physics, both experimentally and theoretically. It doesn't appear in electrodynamics to this day. I have been accused, because I work in free energy systems that can permissibly put out more energy than you yourself have to input. They don't put out more than they get in. They put in more than you input. They get the other from outside. Been accused of talking perpetual motion, as is every other scientist who's tried to study the area. You want to know who really believes in perpetual motion machines? Who teaches them from a platform? Every PhD in physics, every PhD in electrodynamics teaches that the electron and the proton create from nothing all the energy and all those fields that source charge produces, reaching across the universe. So you want to know who really advocates perpetual motion machines? Ordinary science. The reason is they assume an inert vacuum. No place for them to get any energy. So that means they create it all. But they just call them the source charge, and the energy pours out, and it continues to pour out forever, never quits. But you can't produce an overused machine when you've got all kind of free pumps producing all this energy. It's ludicrous. This really is what's in electrodynamics, ladies and gentlemen, so help me goodness. The spin of a particle, we measure transverse waves. Yes, indeed we do. Our instruments measure transverse waves. And that's not at all what comes in from the vacuum. What our instruments measure is electron wiggles in the wires, like we're measuring in wires. Now the electrons in the wire, look at the little bottom diagram there, are spinning. And ahead of them in the wire, they got all these other electrons pushing back on them. So they can't go that way. They got too much forcing back on them. And they're spinning, so they act like a little gyro, and they precess side to side, which they do mostly. That's in the textbook. Electrons move down the wire in a current at about 4 inches per hour in a nominal little old circuit. The signal goes down the wire. If it's inductance and capacitance free, it's the speed of light, and since it's really got a little bit of that, a little bit less than the speed of light down the wire. The electrons don't move like that. They move about 4 inches per hour. So the electrons move most of their movement side to side, and that's what our instruments measure, and that's what they detect, and that's indeed the detected measurement, transverse waves. And that's reasoned together. If they really are little gyros, and they really are precessing, and all we're measuring is precession waves of the electrons, the restrained electrons, then we have just proven that the wave coming in from the vacuum, the perturbation from space that disturbed them, was longitudinal. Or else you got to throw out all gyro theory. And you got to throw out electron spin and a few dozen other things. So what we have done, when they started this business, the vacuum was considered to have mass in it everywhere. So whatever came into the wire was considered just to be fluid shaking, and all we were doing was measuring the shaking fluid as it came in from space. Very reasonable assumption for that time. After we found out better, we never changed a thing. We never changed a thing. Next slide, please. Oh boy, now this is a good one. Maxwell's equations, of course, were highly restricted by Heaviside and a couple other folks. But Maxwell himself and Faraday made some enormous errors. They were legitimately made at the time. These were not diabolical. They're not a conspiracy at all. They were the best knowledge of the time. But today I want you to see how strange they are. Faraday thought that his lines of force were actual physical strings in this physical matter that filled all space, they thought. And so these physical strings, when there was a electromagnetic disturbance in the ether, what it was these strings. These were taut strings. These strings were twanging. And that's where the notion of the transverse wave in the ether came from. This Faraday's twanging strings. And Maxwell says, and I sort of paraphrase the quote, I set about to capture exactly the thinking of Faraday. Now, he did have to replace those strings with tubes. Taut tubes of force, but that's pretty close to strings. And so the whole notion of transverse electromagnetic waves in space is based on twanging strings. And so help me God, all the time I've been alive, I never saw a twanging string in space yet. Plumb, like the Cajun says. Next slide, please. But then we never changed the models. We never changed the equations. What really happens? Well, Maxwell ignored half of the energy and half of the waves. Threw them out because it didn't know anything. You see, the electron hadn't been discovered at the time. Nobody knew there was a thing called an electron. The atom had not been discovered. The molecule was a formless blob. Everything was fluid dynamics. All they wrote was shaking fluid. They didn't write electron spin theory and nuclei of atoms and all of this. None of that stuff is in there. So what they had ignored the following. When I produce a disturbance in a transmission wire, what I do is I disturb the electrons up there. They wiggle, waggle, and precess sideways, and so do the nuclei. Now, the nuclei is a lot heavier than the electrons, but they recoil with equal energy, else I got to throw out Newton's third law. Well, they do recoil because we can measure that, and any physicist will admit that, but that isn't included in electrodynamics. Because now what happens? The electrons reach the surface of the wire and stop. In other words, they are embedded with this energy exchange in the surrounding ether or vacuum, and they shake the vacuum flux. If you're in quantum mechanics, they shake the zero-point energy if you're in continuous wave theory. Whatever they do, they shake up the troops in this space. Whatever space is out there. That's what's perturbed. And at the same time, the nuclei, having positive charges, going in the opposite direction, equal momentum, much less distance because they're highly damped because of the large mass, but they deliver equal amount of energy to the perturbation of the vacuum. So the vacuum, medium, whatever it is, gets a wave of expansion, the two pushing apart, and the two coming together. That's what Tesla called his expansion rarefaction wave. It's just like a sound wave, and that's exactly what it is. It is an electromagnetic sound wave. But of what? What's shaking? I'm going to show you in just a moment. Next slide, please. Well, then comes along, because in electrodynamics, you see, we still assume the material ether. We still teach it at every university in the United States, including right here in Seattle. Never changed. Still in all the equations. Do you remember when your professor told you that at each and every point in space there was a unit point coulomb of charged mass, there was a unit north pole of magnetically charged mass, and there was a unit kilogram of mass sitting at each and every point in space? Man, that's a lot of mass in space. You mean that empty stuff out there has got mass like that everywhere? And what the equations describe is how those unit masses and unit charges move if they were there, which they are not there. But they are still assumed to be there. So this shaking field, there's never been an electric field in a vacuum, never will be. This has been well known since '59, been pointed out before then, but accepted since '59. But it never changes electrodynamic teaching. There's never been an electric field in a vacuum. There's never been a magnetic field in a vacuum. There never will be, because they're force fields, and they require all those point coulombs and those point unit masses, and the Michelson-Morley experiment killed those dudes in the late 1880s. Killed them dead in a mackerel. And what did the electrodynamicists say? Now, I got sympathy for those fellows. I'm being a little funny, but I'm not really condemning those guys. They had a formidable job. There was only about 3 dozen of them in the world at the time. And what they said, fine, they wound up this way. Okay, if we don't have an ether, a material ether, we're not using one. They never changed a single equation. They never eliminated the material ether from the equations or the assumptions of the material ether. And every school in the Western world is still teaching that same old material ether that went down the tubes 110 years ago. Now, how long is it going to take our guys to change something they already know and admit is wrong? Another 100 years? Maybe. Next slide. Here's the definition, the way they define it. The field, the potential. The scalar potential. Common old voltage in the vernacular. It ain't even a scalar entity. 1903, Whittaker showed that it's just made of a bunch of longitudinal wave pairs. Hey, longitudinal wave pairs. A wave going one way and its phase conjugate going the opposite way. It's time reverse twin. It's anti-wave. Wave, anti-wave pairs. The thing is a multi-wave entity, and so a multivectorial entity. It ain't even a scalar entity. But it's called a scalar entity. Now, what is scalar is the amount of energy that an intercepting point coulomb is. If you stick one out there, it diverges the fluid flow around it. And so these waves all have to diverge around it, and the amount of energy in that divergence at that point is considered to be the magnitude of the potential. Ain't no such thing. They're the magnitude of how much energy is diverged out of the potential. They have nothing to do with the magnitude of the potential. By the way, let's reason together. If I have the tiniest of flashlight batteries and it puts out 1/4 of a volt, and it puts out 1 milliamp, how much energy can I draw from that little bitty battery, the potential that's in that battery? How much would you like? Would you like 6 times 10 to the trillionth power joules? The formula, ladies and gentlemen, in ordinary electrodynamics is phi Q. Phi is the potential. Q is how much collecting charge you have. And the amount of energy you can collect from that depends on how much Q you got. If you got a itty bitty 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 bit of voltage, just add enough Q, and every single bit of charge will collect its little piece of energy, and it'll just keep adding as you add more charge. So from any finite non-zero voltage or potential, you can, in theory, collect any amount of energy you wish to collect. And we are not allowed to do free energy? Oh, come now. Let us reason together. Next slide, please. So the fundamental definitions got wrong. Well, they got worse. They went from there to worse. Here's a common little old circuit. Remember, this was put together as fluid flow. Now, I'll come back to how much energy is really going here. There's about 10 to the 13th times as much energy flowing in this circuit as what we normally are taught to calculate in our university courses. And we'll show you how that got changed and thrown away. What we do is the electrons, we put a potential on the electrons on the top wire. The potentials are higher, and so the electrons are energetic, and there's more on the back end than on the front end, so that's a gradient, and that's an E field, and it pushes the electron forward. And in the model they use, where the electrons actually go ahead and travel on through the circuit, actually the energy pushes on down to the succeeding electrons. We go through the resistor, and they lose their little potential in the banging and clanging, and they shake off some fields we call heat. Now, when they get down to the bottom, they got none of those extra potentials left, like the Cajun says. They done exhausted all of that. They don't got nothing pushing them. So they're just hanging there like so much residue. But now your problem is, the way we're taught to build circuits, you got to push that little dude now that's hanging in the middle of your way all the way across that bottom line back to this battery here that I show on the left. And you got to shove him back up all the way through against the back EMF, banging and clanging and knocking the source particles every which way. Well, it turns out that half of the energy that's delivered to the circuit has to take him back up to kill the dipole. And the thing furnishing the energy is not the battery at all. It doesn't furnish nothing to the circuit. There's no work on the circuit at all. Sorry about that, but it's true. What the battery does is, when you fools that we are, when we build this circuit and we run the current back through the back EMF, we destroy the dipole which already we know from particle physics for 40 years has been pulling energy out of the vacuum and running it freely down the wires. We destroy the gusher that's furnishing the energy to run the circuit. We kill the gusher. Strangle that dude. And so what we have to do, the chemical energy in the battery then has to do some more work on some more charges to bring them back together and restore the dipole so it can pour out some more energy. And what we do is we have a big old sumo wrestling match right there, and we kill that thing as fast as it forms. And since we kill it with half the energy that came out of the vacuum for free, the best we could ever get is half left in the circuit, and that's 1-to-1. That's 100%. That would be superconductivity. And so damn fools that we are, we have to keep putting all the energy in there to get anything down through the resistor at all. And that's what we teach every electrical engineer in the country to do. And it's really that simple. Next slide. We'll show you some more here. Now, boy, we have been trained now with very clever artwork and artful dodging to teach all our electrical engineers and many of our electrical physicists that power and rate of energy flow are the same thing. So when they talk about batteries furnishing power and generators furnishing power, power is not furnished to the circuit. Power develops in a component that's scattering something, like a resistor, for example, or changing the form of the energy. No generator and no battery furnishes any power anywhere. Now, energy, that's a different thing. But what we did, if you look at the energy flow, which was added after Maxwell by Poynting and Heaviside, Poynting, who got the name for it because he published in a prestigious publication, got the direction wrong, got the magnitude wrong by about 10 to the 13th. Heaviside corrected all that. So they used Heaviside's theory, which is what we teach today as Poynting theory, only we give it Poynting's name. And so what happens is, here's two wires, standard wires in a circuit or a transmission line. And this is right out of a standard garden variety electromagnetics book by Krauss, as a matter of fact. Actually, the energy flow fills all space around those wires. And I'm going to be in a perfect situation. I'm going to have these wires without none of them capacitance and without none of them inductance, just for Gedanken experiment. And so all that energy is going to be going at the speed of light. Only a tiny, tiny tad of it, by the way, it reaches out to infinity in every direction. And these are the contour lines for the level of the power, as they call it, if you were to intercept it and use it at each point around there in those contours. This is right out of the standard garden variety book. Now, the only part that gets in the circuit is a little tiny part that strikes the surface charges in the wire. Remember what intercepts and directs energy and causes it to change and diverge? It's those little charges. And basically, it's the surface charges that get exposed to that little sheath right around the wires, or if it's a component, right around the component, and diverges part of it in there to power up the electrons in the circuit and form the J phi, which is the Slepian vector. Now, what we have here is an embarrassment, like the Cajun says. Plumb embarrassment. The reason is, if you calculate the energy flow, how this little old bitty circuit, maybe with a little old bitty battery powering it, it's enormous. Unbelievably enormous. And it reveals that we build the poorest thing in the world for electric circuits to intercept and catch energy and use it. I mean, I can't think of a word bad enough to describe how terrible the collection efficiency of our accepted circuits is. Think of the worst one you can and make it 10 times worse. You're still shy. Well, next slide, please. There was an answer to that. Get rid of the problem. You got a problem? Get rid of it. Sweep it under the rug. So Lorentz taught us a little trick. We put a little old closed surface cylinder right around that wire there, or some component, if we're looking at a component, and we iterate that Poynting vector right around all that whole closed surface. And all those components that didn't hit nothing and didn't get diverged, they passed the same speed and the same magnitude and the same direction out the other side. It's a positive vector going in, so negative vector coming out. The integration cancels it. The only vector that's retained is the amount that hit the surface electrons got diverged into the circuit. So it'll match your instrument readings.